All right, let's try to look at a diagram of what could be happening in lab. So we are going to be hooking up a voltmeter. The LabQuest has a probe that's a voltmeter probe, and we are going to hook it up to our two half cells. And so the wires have two different colors. One of them is black and one of them is red. So if we hook the black one up to the anode and the red one up to the cathode, we will see a positive readout. We don't know which metals we're using, so this particular drawing that I found, we have silver and we have copper, and so we know that silver is the cathode and copper is the anode, and so we get a positive readout. If you hooked your LabQuest up to the two different metals and you get a negative readout, then you know that this is reversed. You have the red wire hooked up to the anode instead. So just make a note of whether the readout is positive or negative, and then you can figure out later what that means. So the positive is supposed to be going to the cathode, the negative is supposed to be going to the anode. If you get a negative readout, then those are reversed. So this data is taken from a table of different potentials. So in lab, we're going to be making our own table of potentials. So let's just look at what happens using a table that is already known. So we have known metals and known potentials here. So let me show you a copy of the, we have a copy of the whole table in worksheet 20 for this class. I'll show you what that looks like here. So the last page on worksheet 20 in the class has a table like this, and that's where I got these values. All right, so we have these things taken out of that table. We have the silver being reduced. So the table is always a table of reductions. So we have some sort of metal ion with however many electrons it needs going to the solid metal. That is the half reaction that is shown in the table. And then the table's organized so that the larger, more positive numbers are higher up on the table, and then the smaller numbers are lower down on the table. Arbitrarily, hydrogen ions going to hydrogen gas is assigned a value of 0. So anything that is less favorable than hydrogen, will have a negative number. So both of these are positive numbers. They are more favorable. The reductions are more favorable than hydrogen, so they're both positive numbers. So the higher up on the table it occurs, the larger the positive value of E you see on the table, the more favorable this reduction is. So it is more favorable for silver to get reduced to silver metal than it is for copper to get reduced to copper metal. That's less favorable compared to silver. So the less favorable one is not going to happen. So instead of having, both of these can't happen at once. So the more favorable one is going to happen. The silver is going to get reduced. The reduction is happening at the cathode over here. So that's the silver cathode. This is what's happening at the cathode, is that the silver ions are getting reduced to silver metal. So this is more favorable. I went ahead and copied it exactly the way it looks over here and kept the number the same. Since this is less favorable, this is not going to happen, and so the copper, we're going to reverse it. The copper metal is going to get oxidized to copper ions, and electrons are coming off of the copper. And since this is the opposite of what we had in the table, we have to change the number to the opposite, making it negative. And then if you add these two, then this is overall what's happening. The potential is overall 0.46, 0.8 volts minus 0.34 gives you 0.46. That's what we see on the voltmeter. We've sort of gone from things that we know to what shows up on the voltmeter. In lab, we're going to do the opposite. We're going to take readings off of the voltmeter and come up with this table. So let's try to see if we can work backwards the way we're going to be doing it in lab. So rather than predicting from a table what we're going to see in lab, we're going to see things in lab, and then we're going to make our table. So in lab, we are going to be having 7 unknown metals, and they're going to be labeled A, B, C, D, E, F, and G, and we are supposed to set metal A to 0, similar to how in the actual table hydrogen electrode is set to 0. We're going to set metal A to 0. So we're just going to do an example here so that you can try to use this example to figure out what you're going to do in lab with your 7 unknown metals. So for our example here, we're just going to have 4 unknown metals. I'm going to call them W, X, Y, and Z. And then the very first one, alphabetically, metal W, we're going to set to 0. So we're trying to make a table in lab of the half reaction. Remember, the half reaction shows what's happening with a reduction. So the metal W, we don't know the charge, could be +2, could be +1, so I have it as +N. We're going to add N number of electrons to it to come up with W metal with a 0 charge. So that is showing the reduction of metal W. That's the half reaction, and we are going to set this equal to be 0 volts. So that's our potential of that half reaction. So let's say we go into lab and we set up our cells. We have W set up with the black wire. So the anode is supposed to be W, and conventionally that's written on the left. The cathode is supposed to be written on the right. So if we set a piece of metal W up in a solution of W metal ions, and then we set X, we have to compare it to something, so we're going to choose X to compare to W, and we set that up in a solution of X metal ions. If we set up the red wire to connect to metal X, and we set the black wire to connect to metal W, and we see a positive readout. So we'll see a positive readout of 0.375, then that means that this is set up the way we expect, with the black going to the anode and the red going to the cathode. So this is the way we expect. I labeled the W solution as the anode and the red solution as the cathode. Let's just do this example here that we see a positive number. And the anode is where oxidation is taking place, and oxidation is a loss of electrons. So remember, the mnemonic oil rig, oxidation is a loss of electrons and reduction is the gain of electrons. And then we can also try to remember that R and C both start with consonants, so reduction is what's happening at the cathode, oxidation is what's happening at the anode. O and A both have vowels. So that's what's happening at the anode. So this is what's happening. We have the W, the anode, being an oxidation. So that means it's losing electrons. Metal W is losing electrons, becoming W with a +N charge, losing N number of electrons. And then at the cathode, that is where reduction is taking place. So we have X with a N positive charge getting N electrons added to it to become solid metal X. So this is what's happening in our system here. The overall voltage of the cell, the E of the cell, is equal to the sum of both of these. We've set W to be 0, so that's 0 volts. So normally in the table we have the half reaction being the reduction, and right now in our system we have the oxidation. But since it's 0, we don't have to worry about changing the sign when we flip it. It's still 0 when we do the opposite. The opposite of 0 is still 0. So we have 0 being the anode, and then the cathode is question mark. So then we have a positive 0.375 volts as our question mark. Since that is a higher value than 0, then in our table, this reduction will go above the W. X is going to go above W. So here we have the half reaction of X with a +N charge, getting N electrons added to it and becoming solid X metal. And that would have a potential of 0.375 volts for that half reaction. All right, let's take another example here. We have you setting up metal W and metal Y. and you decide to put the black clip onto metal W electrode and the red clip onto metal Y electrode. And this time the reading comes out as a negative value, negative 0.211 volts. So that means that we don't have this set up in the expected way. We expect the black wire to be going to the anode and the red wire to be going to the cathode. If this is negative, then you actually have that reversed. So you could either switch the clips physically, actually in lab, or you could just write down that this is a negative number so that you know that this would actually be the case, that if you had the black wire hooked up to the Y and the red wire hooked up to the W, then that should give a positive 0.211 volts. So let's go ahead and do the calculation as if it were positive. Again, you don't have to do it physically in lab. You could just draw this little scenario later so that we know that that means Y must be the anode and W must be the cathode. So that means that there is oxidation taking place for metal Y and reduction taking place for metal W. So I've drawn that out here over to the side. I've drawn W in red. It's getting reduced. So we have W ions with a plus N charge gaining N electrons and becoming solid metal W. And that is, again, by convention set to 0 volts. That means that at the anode we have metal Y getting oxidized and losing electrons and becoming Y ions and losing N number of electrons, whatever the charge on Y ends up being. And that one is the one that we're trying to figure out. So I put a question mark there for the number of volts. And then we have that the value, the potential for the cell is equal to both of the half reactions, the anode and the cathode. We know the cathode one this time is the 0 volts, and so we have this question mark, and that ends up being a pretty easy algebra problem to solve. So this question mark actually equals 0.211 volts. So that is for this reaction over here. When you put the reaction, the half reaction that goes into the table is the opposite of this. So we want to have the reduction of Y as the half reaction in the table. So when we change that around, when we write the reverse of this, we have the Y with the N positive charge gaining N electrons and going to metal Y. When we flip this around, we change the sign of the potential. So this is actually negative 0.211 volts, and that would put it below W on the on our table that we're making. And that makes sense because if something's lower down on the table, then it's less likely to do this reaction. It's going to do the reverse reaction, and that is what we see in our setup when we measure it in lab. All right, let's do one last reaction. We got to try figuring out metal Z here. And instead of comparing it to W like we've been doing all along, you could keep comparing everything to W, but I thought I'd try something different and compare it to X. So we had already figured out X, so now we can compare Z to X. And let's say that we put the black wire onto the X electrode and the red wire onto the Z electrode, and we get a positive reading. So we get a positive 0.104 volts. So that means that this setup is the way that we expect, with X being the anode, the black wire going to the anode, and the red wire going to the cathode. So I've labeled these as anode and cathode. And so that means that the cathode is where the reduction is taking place. So the zinc ions are adding electrons and going to zinc metal. And at the anode, that's where the oxidation is taking place. So the X metal is losing electrons and becoming X with a positive charge. So in our table, we figured out that X becoming reduced was a potential of 0.375. So this is the opposite. This is X getting oxidized, so this would actually be a value of negative 0.375. So when we look at our cell, the overall potential for the cell, 0.104 volts, we have to take the value of the anode, which is a negative 0.375. That's what's happening to X. And then question mark is what we're trying to figure out the cathode. What is the value for Z? So when we solve this for our question mark, we end up with a positive 0.479 for our question mark value. So that is the value, let's put volts over here, for what is happening to Z at the cathode. And so at the cathode, this is the reduction. So this is the same way that we would write it in the table. So this will be a positive 0.479. So this would go at the very top of our table. So I've added this into the top of the table. We have a 0.479 for the metal ion Z gaining some electrons and going to solid metal Z. And so if we are reacting Z and X, since Z has a more positive number, it's 0.479 compared to 0.375, then we would expect Z to do this reaction that is written in the table, the reduction, and X will have to do the oxidation, which is what we saw in our experimental setup. So this is the way that you would use the lab data to start comparing different metals to each other and create a table. So what you need to do before lab starts is make a plan for which metals you're going to compare. You don't need to do every single one like we did here. We never did Z versus Y, but we did enough so that we get values for the table and we can order them in the table. So you don't have to do every possible combination. You just have to make sure that every metal you have is done at least once so that you can calculate the values and assemble a table for part A of the lab. So I tried to show how each of these readings is going to be taken once you've made your plan of which metals you're going to compare to each other. Here's how you actually do the comparison. We're going to have a well plate, a plastic well plate with a bunch of different wells, I think 24, I think there's 6x4 or something like that in the plastic plate. And each of these can hold some liquid. So you're going to decide what to put in this well. So maybe the first well you start with metal A. And so well A will get a solution of A metal, whatever solution is labeled vial A, that has a solution of metal ions, metal A ions, and you'll put that solution in there. And then you'll also have a solid, like a packet of labeled plastic pockets labeled A through G, and those will have pieces of solid metal in them. And so you would have to get the matching metal, metal A, and put it in that well as well. And then the same thing for B, you would have some of the liquid solution of metal B ions put into well B, and then a solid piece of metal B into that same well. And then connecting these two, this little purple arch is supposed to be a piece of string. So you would cut a piece of string about 5 centimeters. That's like about the size of a cracker, saltine cracker or something like that. So you'll have it that long, and then you'd put it on a watch glass and put several drops of potassium nitrate solution on the watch glass to make sure that the string is wet with the salt solution. And then you could go ahead and put one end in well A, one end in well B, so that it bridges those two wells so that there's a connection there. And then go ahead and clip the alligator clips from the LabQuest voltmeter probe onto the two electrodes and see if the reading is positive or negative, and see what the value is. And then you would record that to get the potential of your cell that you just made. And then you just repeat that for different combinations. Maybe now that you've compared metals A and B, you want to compare metal A and C, or maybe B and C, whatever you want to do there. And so that's the plan that you're going to try to make up before you come to lab. Make a list of the different pairs that you're going to try out. And then this is how you set up and get those readings. Maybe save one of the rows of the well plate to be able to do part B. Let me go ahead and see if I could draw that out. All right, for part B of the lab, hopefully in part A, so make sure in part A you have something where you're comparing the A and C metals as one of your trials that you're comparing. You want to compare metal A and C and know the voltage difference between them if you just have one single cell set up. So you have the piece of string connecting them, the metal A inside liquid A, metal C inside liquid C, and then the two clips of the LabQuest voltmeter probe hooked up to the LabQuest to get a reading. So that is a single cell. We're going to try setting up some cells in series. So save one of the rows of your well plate, and then you're going to make a row like this where you alternate wells A and C and A and C and A and C. So you'll have 3 wells that have liquid A ions in them and a piece of A metal. So you have that 3 times. 3 where you have C ion solution and then C metal in there. And then you're going to need 3 salt bridges. So I have, if you can see the purple arches there, you're going to need 3 pieces of string that have been soaked in some of the salt solution and the potassium nitrate solution. And so we have that set up. And then the LabQuest alligator clip can clip to the metal that's in the first well A. And then the second well, the C metal and the A metal, use a different alligator clip that's not hooked up to the LabQuest. Just a single metal clip to make those 2 pieces of metal clip together, just so that the electricity can flow through them. And then we have a salt bridge to the 4th well, which has a piece of C metal and a C solution in it, and that's where the other LabQuest alligator clip should go. So we have 2 cells, and they're in a series, and we're going to see what the voltage, what the potential reading is for that, having 2 of them in series. And then we'll go ahead and unhook this one and have 3 in series. All right, so here we have 3 in series. So instead of the 4th well having a piece of metal where you've hooked up the LabQuest clip, instead clip that with a separate clip, one that's not connected to the LabQuest. We're going to clip the pieces of metal between C and A together here. And then we have another salt bridge, and then this last well over here, that piece of metal is what can be hooked up to the LabQuest. And then we can get a reading when we have 1, 2, 3 cells in series and see what the voltage is for that. So these values should be additive. So you're going to show what you calculate, what you predict the value should be, and then report what value you actually see for this part B of the lab experiment.